Hi everyone, I'm Tom Roussel. I did my PhD in CINaM, and during my PhD study, I had the opportunity to have a collaboration with European partners, and especially the University of Pavia, University of Jena, and University of London. And we investigate magnetic nanoparticle using cancer thermotherapy. So I would like to thank Nick for the invitation for this flash talk, and I will talk about these papers that get recently accepted in ACS Material AU. So more and more nanoparticles are currently used in medicine, and electron microscopy is a powerful tool to understand nanomaterials, especially to characterize morphology, structure, crystallinity. Electron microscopy is now necessary to really understand and characterize this material that are used in a patient in hospital, and this is becoming mandatory to really understand how they behave. So to investigate their morphology in their native environment, liquid TM is now becoming a high topic, and it's a powerful technique to study the particle in their native liquid environment. And in this project, we use the Poseidon sample holder to perform liquid phase TM. So we are studying magnetic nanoparticles that are used in clinical phase in hospital in Barcelona. And these magnetic nanoparticles are made of a polymer matrix. It's a sugar, it's a dextran with iron oxide core that are embedded inside the polymer matrix. So first we perform standard TM, and we observe two populations in a sample. So as you can see in the right circle, we have a lamellar structure here, and in most of the place. But we also observe a few nanorods that you can see in the square, here and here. And in standard TM, we also observe some iron oxide core that were dispersed all around the sample. So this was the first observation we have done with standard TM. Afterward, we went to cryo-TEM, and once again, we observed the same morphology with the two species, the lamella here, almost everywhere on the sample, and in some part, the small nanorod. But compared to previously, we did not observe any iron oxide core, like here, like on the background. In the cryo-TM, we did not observe any of that. Then we continue with liquid TM, and we had similar observation than with the cryo-TM. So we observe the lamella and the nanorod. So this let us know that with the standard TM, we have artifact of sample preparation where we can observe a single iron oxide core in the solution, which is actually wrong. So with cryo-TM and liquid TM, we can really study the particle in their native environment. So yeah, as I mentioned, the limitation of standard microscopy for characterization of particle in solution is now present because we have a dry sample preparation that can produce artifact. And thanks to liquid phase TM, we are allowed to study and to have the images of the nanoparticle in their native liquid environment. And then from this population, one question arises: is the nanorod a side view of the lamella? So to study that, we perform tilt angle TM to see if at different angle we can see that the lamella become a nanorod. So we shifted from minus 50 degree to 0 to plus 50. And if we follow, for example, here in a yellow square, the nanorod, it's still a nanorod with different angle. That means it's really a different species, and it's not a side view of the lamella. So in this case, the electron tomography, the 3D electron tomography, demonstrates that nanorod and lamella are distinct phase in the solution. And the lamellar structure is more predominant than the nanorod. That means we have few nanorod and more lamella. Then to study the crystallinity of the sample, we investigate by high resolution TEM the crystallinity. And we can see that in the lamella here on the left, we have iron oxide cores that are inside, but also we have some polycrystalline phase. It's a little bit hard to see on the picture, but here we can see the different lattice which are oriented in different angle. And for the nanorod, we have a single alignment of the crystallinity, which make it monocrystalline with the iron oxide core also attached on the nanorod. And then we study the diffraction pattern, where we see the diffraction ring of the sample. And on the ring 1, 2, 3, 4, these rings are representative of the magnetic and manganite. That means the iron oxide core are crystallized in these two spaces of iron oxide. So with the diffraction pattern, we can confirm that the sample is composed of magnetite or manganite in the dextran matrix. Afterwards, to be sure that this nanorod and lamella are composed of iron oxide core inside, we perform bright field and high angle annular dark field STEM images to study the composition of the particle and also the core-to-core distance inside the particle. So from the bright field, the phase contrast, as you can see here, with enlargement, we have the presence of the nanorod that are shown in black because they are composed of heavy element, we guess, the iron oxide. And then when we shift to chemical contrast, so HAADF, the iron oxide become clearer, and that means here and here we clearly see that they are the same. So that indicates the nanorod are composed of iron oxide core, and the density inside the nanorod is higher than in a lamella. Afterwards, to investigate and measure the distance of this iron oxide core inside the nanorod and the lamella, we measure in the liquid TEM images the distance between each iron oxide core, because this distance is really important for the magnetic nanoparticle concerning their heating properties. If we have agglomeration of iron oxide core, there is a reduced transfer from magnetization to heating. And these particles are used for thermotherapy. That means we applied external magnetic field, and this magnetic nanoparticle will move really quickly and produce heat that will kill the cancer cell. So to understand the relation between the inner particle and the magnetic properties, we measure this distance, and we can see that in the lamella, so here, the distance between the two iron oxide core, two neighboring iron oxide core, is around 6 nanometers, while in the nanorod, the distance is closer, and it's mostly around 4 nanometers. And so we show that the density of the iron oxide core is higher in the nanorod than in the lamella. But in our case, the sample is composed of around 80% of lamella and only 20% of nanorod. So we have particle iron oxide core that are well dispersed inside the dextran matrix. And to correlate the magnetic properties with the morphology and the crystallinity, we perform Hunker plot data that indicate there is a weak demagnetizing core-core interaction field. So basically, when you have iron oxide core in a close distance, there is a negative effect that will reduce the magnetic field. And as we can see on this plot, here is a linear shape. And if we are below this line, that means there is a demagnetizing effect. So this demagnetizing effect is always present in magnetic nanoparticle because the core to core distance induce this effect. But in our case, the demagnetizing effect is really low. And we can also measure this demagnetizing effect with this graph. And basically, it's a magnetic interaction between two particles around 5 kiloampere by meter. And this measurement is really low. That means the demagnetizing effect is small in our particle. And we demonstrate that the heating properties of this particle are almost 60% more efficient to transfer magnetic properties to temperature to destroy cancer cell. So we show that there is a correlation between the magnetic properties and the TEM that highlight the weak demagnetizing interaction field is due to the particle in a dextran matrice that are uniformly well-dispersed iron oxide core on the lamella. And the distance between the iron oxide core in the lamella is really a key parameter for this type of nanoparticle. So to conclude, the liquid phase TEM offer real-time imaging of nanoparticles in their native liquid environment, and we could really investigate the morphology and the size between this iron oxide core inside the dextran matrix. And thanks to the magnetic properties, we could have a correlation between the structural information obtained from the TEM and the magnetic properties, which allow us to have a deep investigation of this nanoparticle for medical application. And this helps us to understand how to further design this particle for translation. So we can now have optimization based on the present study that highlights the importance of the core-core interaction in this magnetic nanoparticle, which are currently used in hospital and demonstrate high performance. So thanks for listening and hope it was clear.